Alright, more trig stuff, but this time we're going to be talking about inverse trig functions and how to differentiate these. Now, none of these 6 basic trig functions are one-to-one. One-to-one meaning that for each x value there's only one y value, right? If you think about the graphs, they're periodic, so there are multiple x value for the same y value. So really then, none of them have an inverse, which is a function, right? Function, keeping. However, what we can do is use domain restrictions to make trig functions one-to-one, so that they do have inverses that are also functions. So in this course of AP Calc, we will only deal with the inverse trig functions for sine, cosine, and tangent functions. That's definitely enough. So the inverse trig function is this. It's called arc sine x, or sometimes they'll use this notation, sine negative 1 of x, like that. Okay? Don't confuse this though. Not equal to 1 over sine. That's the reciprocal function. Okay? That would be sine x all to the power of negative 1. Okay? So that's why a lot of textbooks rather use this thing called arc sine instead of sine negative 1 of x. So remember, if we were to rewrite this, then that's equal to x equals to sine y. And same thing for all the other ones, arc cos and arc tangent. Now, to make them functions, we have to put limits on the domain and the range. So for the arc sine function, the domain is negative 1 to 1, which should make sense because the regular sine function has a range of negative 1 to 1. But here we have to limit the y values, and we arbitrarily chose to limit them between negative pi over 2 and pi. For cosine, we arbitrarily chose 0 to pi, and for arctangent, same as sine, from negative pi to pi over 2. So by doing that, we can then graph the indicated inverse trig functions in the coordinate planes below. For the arcsine graph, we go from here to there, with a nice curve like this. So think about how we were to take the regular sine function and reverse it around. For arc cosine then, starting at 1, right, like that. And then arctangent's graph looks like this, because these are my asymptotes for the tangent graph. And I'll get a graph that looks like this. So notice arctangent's domain is all real numbers, but the range is limited to between negative pi over 2 and pi. If you want a geometric representation of the range values, then this is the picture for you. Notice arcsine and arcsine and arctangent go from negative pi over 2 to pi over 2, where arc cosine goes from 0 to pi. Now the two biggest mistakes are this. The biggest mistakes that students make with inverse trig functions are putting in the inappropriate range values for an answer, or putting more than one range value for an answer. So for example, arcsine of negative 1/2 is equal to negative pi over 6. And this is the one and only correct answer. Okay? Even though you learned before that when you did arcsine of negative 1/2, most often you got these two answers, and this was in the domain of 0 to 2 pi. But unfortunately for us, we limited our domain here for arcsine to be from, yeah, you got that right again, negative pi over 2 to pi. Okay? So because we limited it, this is the only correct answer. Alright, turn the page. So if I ask you to do example number 2, I think you should know how to do that now. So explain why arcsine negative 1/2 equals to 11 pi over 6 and 7 pi over 6 are not true. Once again, because of our range restriction. The range restriction on inverse sine is from negative pi over 2 to pi over 2. And these are outside the range. Alright, so without a calculator, can you go ahead and evaluate these arctangent, arcsine, arccosine values? Arctangent of 1 means what angle gives me a tangent ratio of 1. And hopefully you remember that's pi over 4. Remember everything is in radians. What angle gives me a cosine ratio of negative 1? Hopefully you remember that. With the unit circle, that's pi. In this case, what angle with a sine ratio equaling negative root 3 over 2 is this? And in this case, you can think about where sine is negative down here, root 3 over 2. Well, unfortunately for us, there are two answers, but the only one that works is the one that's in our range, which is from negative pi over 2 to pi over 2. And so I believe this answer with a reference angle of pi over 3 becomes negative pi over 3. Because that's the angle starting from the initial arm, and this time going clockwise down pi over 3 radians. Arcsin of 2, I hope you said this doesn't exist, because there's no angle when I take its sine value giving me the value of 2. Opposite over hypotenuse can't be bigger or equal to 1, or can't be bigger than 1. So those are ones without a calculator because they were nice special angles or special ratios. These are not, so just bring out your calculator and calculate, please. Arcsin, so shift sine of 0.3 is just equal to 0.305. Do the same thing for arctangent. You should be practicing, not just looking at me. Getting used to your calculator. That's negative 1.19. Okay. Now, simplify without a calculator, it says. So, Sine of Arc Sine. Hey, what do you know about that? Hopefully you remember. Sine of Arc Sine. That's, those two things just are inverse of each other. They just kind of cancel each other out. You get root 3 over 2. Tan and arctan, right? Inverse functions back to back. Get 3. Arc cos and cos. Oh yeah, same thing. Pi over 3. And then arcsine of sine, that's 11 pi over 6. Right? No. What did I do wrong here? Tricky. Well, sine 11 pi over 6, that equals to the ratio negative 1/2. And then I'm asking you to find the arcsine of negative 1/2. And yes, remember the range value has to be between negative pi over 2 and pi over 2. And that's why 11 pi over 6 does not work. We know this from, I think, example number 1 or 2, that this equals to negative pi over 6. Okay? So tricky. Alright, you should also be able to solve these. And once again, this is all just pre-calculus stuff. We haven't done any calculus yet. So to get rid of the arcsine, we can then take sine on both sides, right? And the sine of pi over 2 just gives us the value of 1. And so we have x squared minus 3 equals to 1, or x squared equals to 4, or x equals to plus or minus 2. So that's how you can solve that. Okay? This is important because I'm going to ask you to try to sketch these right triangles to find different ratios. So what does this mean when I say x equals to arc cosine of 2 over root 5? You could be thinking, if I take cosine on both sides, that's cosine x now equal to 2 over root 5. So if I were to draw a triangle and x was now my angle in question, cosine means that the ratio of the adjacent to the hypotenuse side is like this. And that allows me to find the length of the missing side by Pythagoras. 5 squared minus 2 squared, that's just, I believe, 1. And now with the picture complete, I can now find tangent x, because tangent x is defined as opposite over adjacent. There you go. 1/2. Now, How about the next one? Given that y equals to arcsine of x, can you then find cosine of y? So, in this particular case, if I were to rewrite this as sine y equals to x, drawing a triangle now says, hey, y as my angle, sine is the opposite side over the hypotenuse side. Using Pythagoras, I should be able to figure out the missing side down here. 1 squared minus x squared, that's 1 minus x squared. And now with my complete triangle, I can figure out cosine of y, which just happens to be the adjacent side over the hypotenuse, or just root 1 minus x squared. Okay? Now, we're going to use this to help us now find the derivative of arcsine of x. And to do this, I'm going to ask us to go to the 9.4 supplement in the back of your book. And here we've already talked about what these functions are. Just as a reminder, once again, note that the sine negative 1x does not equal to 1 over sine x. We talked about all this one-to-one stuff. Here are my graphs again. So let's go ahead and actually find the derivative of arcsine. Okay? So to do this, what I would like us to do is actually apply sine to both sides. Sine of sine, arcsine. And of course that just gives us sine of y equals to x. Remember what we did earlier? When we had those triangles? We'll come back to that. But now in order to figure out this derivative, I'm trying to figure out y prime. So now I'm going to actually ask you to take the derivative, but take the derivative implicitly. So the derivative of sine of y is cosine of y with an extra, you got it, dy dx. That's implicit differentiation or chain rule. And the derivative of x is just 1. So therefore, dy dx is just equal to 1 over cosine of y. Now here's the funky thing. What is cosine of y? So going back to this little step here, remember? Talked about a triangle. Can you also draw out the right angle triangle here? Boop, boop, boop. Here's my angle y. Sine of y is x over 1. We did this already, so I'm just going to quickly write this down. And then once again, can we now replace cosine y with adjacent over hypotenuse? So in this case, this just equals to the 1 divided by the square root of 1 minus x squared. So, key thing here now is if I gave you the arcsine or inverse sine of the function x, its derivative is 1 over the square root of 1 minus x squared. Okay? And this is the same procedure we need to do to find our cosine's derivative and also our tangent's derivative. So can you try this on your own? I will do it myself, but you can come back and double check your work with me. Go for it. Derivative of cos is negative sine y dy dx. So dy dx equals to negative 1 over sine of y. Where's my triangle? Where's my triangle? Cosine in this case is x over 1. So this becomes 1 minus x squared. And sine of y, opposite over hypotenuse. In this case, we have a negative of the same thing. So big box. Y equals to cos negative 1 of x. Its derivative is negative 1 over 1 minus x squared. And then finally, our tangent. Same business. You should try it on your own. This time I'll draw out my triangle first. Tangent is x over 1, so the hypotenuse is 1 plus x squared. The derivative of tangent is secant squared y, with once again implicit differentiation. The derivative of x is 1. So dy dx is actually 1 over secant squared y. Secant squared, well, what's secant squared? That's the same thing as 1 over secant y all squared. Well, what's secant y? Secant of y is 1 over cos, which happens to be hypotenuse over adjacent. So note here, secant y is the hypotenuse over the adjacent, which just happens to be the square root of 1 plus x squared over 1. So this becomes 1 over the square root of 1 plus x squared, all squared, or just 1 over 1 plus x squared. And so we've got it now. 3 inverse trig functions and their corresponding derivatives that you have to memorize. Back to your notes. And now, if you look on page 197, you've got that nice chart that I just asked you to memorize. And of course, the right-hand side here are all the things with chain rule. And of course, things wouldn't be fun without chain rule. So with the remaining 3 examples, can you now actually differentiate these functions? So for number 10, g prime of y, since it's arctangent, the derivative of arctangent is just 1 over 1 plus x squared, but this time x is not x, it's a function, 2y minus 1, all squared. And don't forget that hook-on factor for chain rule, an extra factor of 2. So the answer here is just 2 over 1 plus bracket 2y minus 1 all squared. Okay. I think you should be able to do the rest on your own. So I'm going to leave you now. You try it, then come back and double check your answer. Go. Arcsine's derivative, square root of 1 minus root x all squared. And then don't forget the hook-on factor, the derivative of x to the 1/2. There we go. I can make this look a little bit nicer. 2 root x, 1 minus x. And then finally for number 12, the derivative of arc cosine is negative square root of 1 minus x. In this case, my x is ln of t. And then don't forget the hook-on factor here. The derivative of ln is just 1 over t. So if I wanted to write this nicer, how about something like this? That's it. Okay. Memorize, apply.